Hi, in this video, we want to take a look at prediction and confidence intervals for regression models where we use transforms. Okay, so the big idea for this video is that if I've gone through and I've transformed my Y variable, my target variable, to get a better regression model, in R, when I go to make my predictions, I have to convert the predictions back because the predictions, the fitted values, the confidence intervals, and the prediction intervals are all going to be on the transform scale. But I don't want the transform scale. I want the original observation scale because, you know, when I go to like explain things to people, that's the one that they're going to be ready for. They're not going to be ready for logarithms or square roots or cube roots or anything like that. So what I'm going to do, I'm going to, do my transforms, build my model. Then I'm going to run the predict function. Then whatever I get back from that, I'm going to do the inverse of the transform that I used on the target variable. Now notice that if I transform the predictor variables, the X variables, my independent variables, I don't have to transform anything for the output on those. So, if I've got an X, I transform X, I don't have to worry about that when I use the predict function. But if I transform my Y, I have to undo the transform on the output of the predictions. So the output of the predict function. Be mindful of that as you go forward. Okay, and this example is taken from a modern approach to regression with R. This is the class textbook, which is free for UCF students to download at the school's library. Okay, so let's go ahead and use the circulation data set for modeling. So I'm going to go ahead and I'm going to load the data. And as always, I'm going to go ahead and, since I have an ID column, I'm going to go ahead and use that column as my row names. In this example, for this video, it's not going to come up, but it's a good practice to get into so that when you have to go in and start looking for stuff, when you start seeing something funny, it's easier to spot it. Now, I always like to order my data set by the target variable if the data set isn't too big. I find that also makes it easier to find things, spot things, but you don't have to. Okay, so I'm looking at doing a regression model. Remember, my most important part of building regression models are my scatter plots. That tells me more than anything else if regression is a good idea. So what we're going to do, we're going to take the Sunday variable. So this is the I believe it's the number of Sunday subscriptions, and we're going to take the number of weekday subscriptions, and we're going to predict Sunday using weekday. So the idea here is if we were, let's say, at a newspaper, if I wanted to increase the Sunday subscription, well, would it be feasible to increase the weekday subscription? So if we go through and we do a campaign to improve the weekday subscriptions, would I also be increasing the Sunday subscriptions? If we have a positive slope, then yes, we would. It would be worth it. And that way we could get like a twofer. All right, so of course it's going to be the circulation data. Now, something I'm going to do here is that we have a binary categorical variable. And what I'm going to change the plot character and the color, the point color, by the binary variable. Why do I do this? Because it's a really easy way to change the color. So I'll have black and red and like diamonds and circles on my plots. Real quick and easy way to do this. Notice I'm adding a 1 and adding an 18 on there. That just makes sure it's the values I want it to be. And I'm using the legend to just specify which one is which. So we have the binary vector is for tabloid with a series competitor. And so it'll be a 1 if it's a tabloid with a series competitor, and 0 if it's otherwise. So otherwise means it's either not a tabloid or it's a tabloid without a series competitor. All right, and here's our scatter plot. Okay, so I look at this, and the black looks pretty good for a regression line, right? So like the non-tabloids are up here, or the tabloids without competition are up here, and that's looking pretty tight. Now you'll notice that I only have a few points here. So remember that by having that binary predictor in there, if I'm doing a regular vanilla regression model, I'm changing the y-intercept by having this here, so that tabloid would have the same slope, but a different different y-intercept. So I'm making these, even though I have very few points, I'm going to make the assumption on this model is that tabloid with a series competitor has the same slope of the non-tabloid data points, which is, that may be reasonable depending on the subject matter knowledge. It may not be, but for this example, we're going to run with it. Now, if you take a look at the data, you'll notice that the data kind of looks skewed. See how I got like a lot of points here, and it kind of disperses, lots of points all clustered and bunched up together. I'm thinking this is skewed data. Yeah, I think it is. And it's all positive values. So you know what we're going to do? Let's go ahead and do a log transform. Why am I doing log? Because it's a reasonable one to do for skewed data. Square root would be another possible choice. This is like count data. So a Poisson regression might be reasonable, a Poisson distribution assumption. And when I've got Poisson distribution assumption, the square root transform is reasonable. This is coming from a textbook. Textbook author picked logged. I didn't really question it. I'm just kind of run with it. But if I had misgivings about it, I would use the power transform function in the CAR package and then run summary to get the hypothesis testing off of it. If I saw that the hypothesis said that it's not equal to 0, I would look for something else to do. But here, honestly, I'm satisfied. I've already built the model, took a look at it. It's reasonable. So one of the most important ways to handle models is you look at it, does that seem reasonable? I call this the sniff test. If it passes the sniff test, just like an old shirt laying on your floor, right? Right, guys? You know, it passes the sniff test, you're good to go. No, I don't do that. I take pride in my appearance. All right, so let's go ahead and plot it. So now you'll notice that something I do is I go ahead and I let R handle the transformation for me. I'll put log of Sunday and log of weekday in the formula. This means that I don't have to worry with it. I don't have to mess around with it. I'm good. I'm happy with this. Now, this is a good way to go if I'm in a small data problem. If I'm in big data, I'm going to be doing models over and over and over and exploring a lot of different transforms. I might not want to do it this way. I might want to transform the data and then append it onto the data frame and then start building. But in that case, I would just be transforming that data vector one time. And that would be the advantage there. So let's take a look, see what we get. And you know what? The points look more dispersed and they look like a little bit better in terms of the line. Yeah, okay. I'll go ahead and accept this. Now, I have so few tabloids in here, it's hard for me to really feel confident about this. Remember, if you can pick up one point and move it, then, and moving that point changes your perception of the data, then you don't have a trend. And so let's say if I was to take like this point and I moved it over here, or I moved it, this part, I moved over here. Yeah, if I took this point, I moved it there, I wouldn't see a trend on that line. So the act of making a line for the tabloid data is basically, I would have to be using subject matter knowledge to know that it is reasonable to model Sunday by weekday. If that's not reasonable given the subject matter knowledge, what I would want to do is just throw out these data points and restrict it only to non-tabloid data sets. There's that observations. All right, so let's go ahead and build the model. So here, my linear model for a circulation data set, I'm going to take the log of Sunday, and I'm going to predict it with the log of weekday plus the tabloid with the series competitor binary vector. All right, so here, the predictor variable is log of weekday, not weekday, log of weekday, and then tabloid is going to give me a different y-intercept for tabloid papers and non-tabloid papers. Now, something to be mindful of, anytime I get output from this linear model, it's going to have things on the log of Sunday scale, not the Sunday scale, not the original data scale, it's going to be on the log of Sunday. So any output I get from this function for the y values, I'm going to need to transform. Now, here's something that you need to be mindful of. In R, log means natural log, ln. That means base E. So when I do my transform, I'm not base 10, I'm base E, because it's all about that base, no trouble. All right. So now, let's append the standardized residuals and the fitted data to the data set. So here, I'm taking the standardized residuals and I'm slapping on the data set, because I'm going to use it repeatedly, and I'm going to get the fitted values, put it onto the data set so I can explore it. Now let's look at the residual plots. All right, so let's look at the residuals by log of weekday. If I see a pattern in my dots, I have a problem. All right, I'm not seeing a pattern, so I'm feeling okay. Now for box plots, so here, or sorry, when I get to the tabloid binary vector, so here, remember, this is categorical. This is not numeric. Even though it's in the computer as zeros and ones, that's a categorical vector. Therefore, I can't do a scatter plot, or actually, I shouldn't do a scatter plot. Instead, I'm going to do box plots. Remember, a box plot is a 5-number summary of some data. I've got the minimum, I've got the maximum, first quartile, third quartile, and the median, which since I chose black, you can't see it. But you notice I'm choosing the same colors as I had in my scatter plot. A good thing to do when you do visualizations, that you're going to present to people, be consistent with your colors. That will help your audience pick up what's going on a lot faster if you're consistent with your colors. Also, by making colorful plots, people will pay more attention to it than if you're going black and white. And let's see, there might be a difference. I don't know. There's so few here, I don't really put a lot of weight into the tabloid part of the data. All right, so now let's take a look at the residuals by the log of the observed target value. And I don't really see a pattern. And let's go ahead and look at the residuals by the fitted values. And I really don't see a pattern. I mean, kind of a tail looking thing, but I'm not too worried about that on this. I saw on the previous plot also. I think it's okay. Okay, so now what we want to do, we want to plot the fitted values by the log of the log of the target variable. Now, why do I do this? Remember that these need to be on the same scale. If I've got a good model, a good solid model, this will look like a straight line. So what I'm doing is that if I have more than one predictor variable, it's not as direct to be able, let's say I had 5 predictor variables. If I wanted to do fitted by the first, and fitted by the second, and fitted by the third, and so on, that's a lot of plots to look at. And we're already looking at a lot of plots. If I want to be able to do this kind of like in one more summary method, is that I'll take the fitted values and plot it by the target value of the transform version of the target variable. And if I see a good solid line, then I feel good about my model. If I don't see a solid line, that is a big red flag. All right, and yeah, I mean, it could be a little bit tighter, but could be worse also. Now notice that these are on the same scale, 12 to 14, 12 to 14, and that is not the original scale. So remember, logarithms convert numbers to the exponent in scientific notation. That's true for base 10. Base E that's the right way to think. It's not exactly right, but you can think of logarithms as converting numbers to the exponent in scientific notation. And so in that interpretation, it's not 100% right because it's E, but don't worry about that. We can see that this is pretty far off from the original scale. So let's take a look at ANOVA. So remember, there are 3 types of ANOVA: the summary, function gives us one type, and these are for the hypothesis test of asking if the coefficient is equal to 0, and the intercept might be equal to 0, but usually we don't worry about the intercept when we do hypothesis testing and regression. I really don't understand why, but that's the convention, so I just go along with it. Here we can see that we can be pretty confident that the coefficient of log of weekday and the coefficient of tabloid, so this is the shift in the y-intercept. These are pretty small p-values, so I can be pretty confident that these do not have slope of 0, which means that they belong in the model. Now here, this is asking, should we add the variable to the model? So should we add log of weekday to the constant model? Well, that is pretty small, so yes, I believe we should. Next question, should we add tabloid to the model with only log of weekday and a y-intercept? That's pretty small also. So I conclude that we should add tabloid to the model. And if I look at my R squared, that's pretty good. Also, these are pretty close. And I like to see these close to each other. If they're not close to each other, that's a sign of overfitting. All right, so now let's go ahead and get the prediction intervals and confidence intervals. Okay, so I want to put lines on my scatter plot so I can visually see the prediction intervals and I can visually see the confidence intervals. So what I'm going to do, I'm going to make a new set of weekday values, and I'm going to use those generated values to create a new data set, and then I will run the predict function with the model on that data set. So the data that we make predictions on is called the score data, and that's why I call this score. All right, so, and you'll notice I do expand grid. Expand grid takes all the values in this vector and all the values in this vector and finds all possible pairs. So it's a pretty big data set. So when I get the prediction intervals, what I do, I run the predict function on my model. My new data is the score data. And then I tell it to get a prediction interval. So prediction and interval. Lo and behold. All right, so now what I'm going to do, I'm going to plot my data. Now, on top of the plotted points, so this is the original data plot, I'm going to take the points function and I'm going to put my fitted values, and then I'm going to put the upper and lower bounds of the intervals on top of the original scatter plot. Points takes data and puts it on top of the current plot. So here, up here, this part puts the fitted values on the scatter plot. This part puts the lower bound on the scatter plot, and this part puts the upper bound on the scatter plot. Okay, so now, so remember, this is my prediction interval. So this is telling me that I expect to see 95, so if I kept on collecting data over and over and over and over, I would expect to see 95%, so if I picked a particular weekday value, let's say this particular weekday value, if I kept on sampling for that one weekday, I did it over and over and over, I would expect to see 95% of the observations in this interval. Now that's assuming if it's not a tabloid. If it is a tabloid, it would be within the red. Remember, prediction intervals are like the range of observed values. Confidence intervals is like the interval that I expect the expected value to be in, the average to be within. So now let's get the confidence interval. Remember, confidence intervals will always be narrower than prediction intervals. And this is really the same game. But, oh, there's something I must point out. I must point this out. Something that is super, super important. You'll notice that when I do this, when I plot it, I put an EXP right there. It's not for experience points. It's for the exponential function, the inverse of the log transform. So I'm taking the inverse of the log transform every single time before I plot it. Otherwise, I'm going to get a plot that looks like gibberish. And there's my confidence intervals. So here, the middle line is what I believe the true expected value of y given x will be for tabloid and non-tabloid. And then the vertical difference, the vertical around it, is the confidence interval for the expected value of y given x. And last but not least, I go ahead and look at the add variable plots to see if I can remove a variable. So remember, when I look at add variable plots, if I see a flat line, I am leaning towards removing that variable from the model. And so this is a pretty solid line, so I'm not getting rid of that. Now let's look at tabloids. And we see something of a line. I don't feel as confident about this just because there's so few data points, but I'll go ahead and leave it for now. Well, that's all I got for you. Take care and goodbye.